Hi. So lesson number 8, we're talking about kinetics and we're talking about rate laws. Before we get to that, just a reminder about Zoom and SI. SI is every Monday through Wednesday. There's also tutoring. Um, on the day this is posted, April 22nd, there'll be a quiz. On April 24th, there'll be a review. And then April 27th, test number 1 via Sapling. All this, you can find out more information. I posted a video that'll talk about the procedure for the quiz, test, and the review. The homework for this lesson, lesson number 8, is due April 29th. That's Wednesday at midnight. All right, so let's look at a review. Last time we talked about rates. So a reaction rate is how fast a reaction occurs. Some reactions are fast, some are slow. This can be a big deal. So what we were talking about was, when we talk about reaction rates, we talk about something like this: 0.6 moles per liter per second, or molarity per second. That's how much it's changing. Well, what we learned was that we can relate rates for two different compounds based on their stoichiometry. We said that 1 over A times the rate of A equals 1 over B times the rate of B. Okay, so here's my rate of B, and this small a and small b, these are those coefficients. So this would be 1 over 1 rate A equals 1 over 2 rate B. Okay. Rearranging this, 2 times rate A equals rate B, or actually, sorry, let's just say rate A equals half times 0.6 molar per second, and so rate A equals 0.3 molar per second. Okay, this makes sense because if this is increasing 0.6, this has to decrease at half the rate, because it's A goes to 2. All right, so now let's look at that second problem. The second problem is all about how do we calculate rates. So let's say we have this data. We're told time data and concentration. And so we have 0, 15 seconds, 0.16 molar, and then 0.10 molar. So if we want to figure out the rates, what do we do? Rate is always the change in A over delta T. So this will be 0.1 minus 0.16 over 15 minus 0. Now there's one other thing. Rates are always positive. So that means I could make this absolute value, put like that, or just make this negative, just so that it's always positive. This would give me 0.06 over 15. This is in molarity, this is in seconds. So that's going to get me an answer of 4.0 times 10 to the minus 3 molar per second. Okay, so that is the rate change from 0 to 15 seconds. Let's look at the second time. So we're also asked what happens from 15 to 30 seconds. And so here, we're going to do the same thing. So the rate is going to be 0.07 minus 0.1 over 30 minus 15. Notice how, if I'm only looking at this part, I do final, right? 30 seconds minus the initial. Okay? This gives me 0.03 over 15 seconds. And that's going to get me 2 times 10 to the minus 3 molar per second. So notice that my rate's changing. Okay, So rates aren't constant when we have reactions. Sometimes they change. Okay, so let's look at this in more detail in this next section. All right, before we do that, let's just do a review of lesson number 7. We talked about reaction rates. We said that here, this is how we calculate rate. They're always positive. They can vary with time, as we just saw. We just use this calculation right here. And then it can depend on a number of things, including temperature and catalyst. And that was all lesson 7. Okay, but how do we calculate rates of reaction? Well, one thing we can do is we can use something called a rate law. So a rate law is an equation linking the rate of a reaction with the reactant concentration. Okay, so I'm going to put a bracket around reactant. That means it's concentration. All right, so if we have a reaction like this, AA plus BB going to CC, okay, where these can be any compounds, we're just making it generic. The rate law looks like this. Okay? My rate of reaction is going to be equal to K times the concentration of compound A to some power M times the concentration of compound B to some power N. Okay, so a few things on this. We'll explain each term. The first is that it does not depend on C. Notice there's no C in it. It only depends on reactants. This K is what we call a rate constant. Rate constants are experimentally determined. And they also depend on which rate I'm looking at. If I'm looking at rate of A loss or B loss or C formation. Okay? Now, it's called a rate constant, but it's different than some of the other constants we've talked about. For instance, we talked about C being the speed of light. Well, that's a constant in the fact that it's always 2.998 times 10 to the 8th meters per second. Rate constants are dependent on the reaction itself. All right, now M and N, these are what we call rate orders with respect to compound A and compound B. They can be integers, 0, or fractions. That means they can be 0, 1, 2, 3. You could even have half, etc. What we also say is we have an overall order for the reaction. The overall order is the sum of all these orders. Okay? All right, now here's the key. We do not know the values for N and M based on the equation. Right? They are not necessarily the coefficients. They are different, and they have to be found by experiment. Okay? All right, now this is one rate. We could also have other ones that have other reactants. If we have 3 reactants, we'll have 3 things here. Right? But this is a simplified or a simple one with only 2 reactants. Okay? All right, so this rate law is an example of something we call a differential rate law. So differential rate laws link rates to the concentration. Okay? So for instance, here's one: negative delta A over delta T equals Ka to the M. Last time we talked about what if we make those changes small enough that eventually they get really close to 0. This is called what we call a differential, right? So these D's mean, hey, looking at a very small second in time, right? So instead of saying, hey, how fast are you going over the next mile? How fast are you going in the next second or millisecond or nanosecond, right? These are differential rate laws because they have differentials. Later in the lessons, we're going to talk about integrated rate laws. But right now, we're only looking at differentials. All right, so let's do some practice. Let's say we have this reaction. 2NO2 plus F2 going to 2NO2F. And we're told that it has this rate law. Rate equals K times the NO2 concentration times F2 squared. Notice that those orders, here's 1 and here 2, are not the same as the coefficients, okay? They are not necessarily the same. Okay, so what is the order of this reaction with respect to NO2, F2, and NO2F? All right, so what we're looking for is we're looking for these values here, okay? So NO2, it's first order. Notice that it's NO2 to the power of 1. F2, it's going to be second order because it's F2 concentration squared. How about NO2F? Do we see NO2F anywhere in this rate law? No. So that's the same as NO2F to the 0, because anything to the 0 is equal to 1. And whenever we deal with products such as NO2F, they'll always be to the 0 order. Okay, and the last thing we want to know is the overall rate order. The overall rate order is the sum of all these other ones. So I have 1 plus 2, and that gets me 4. Okay, so how do we determine rate laws? We'll deal with that next lecture, but for now we're just going to look at rate laws. Okay? All right, now let's look at another reaction. NO2 plus CO goes to NO and CO2. Okay? By the way, here's another example of a rate law. I say, hey, it could even have a third reactant. Okay? The ones usually we deal with have 2 reactants, but we could have 2. Okay? Or we could have 3. So this reaction here could have this rate law. The rate equals K times NO2 times CO. This would be to the first order with respect to both. Or it could be this one with second order for CO, or this one with second order for NO2. Or it could be to the first power or the 0 power, right? In that case, these just go away, and I get KNO2 and KCO. And so I actually have a lot of possibilities. But typically, we'll either see things to the 0 order, the first order, or the second order. Okay? But remember, and I'll stress this again, it's not dependent on the coefficients in the equation, right? Just because there's a 1 in front of this NO2 doesn't mean that the NO2 is to the power of 1. It could be to the power of 0, 1, 2, or other possibilities. Okay, so let's see what happens, right, to this rate. So right now, we're going to say that this reaction has this rate law. So rate equals K times the concentration of NO2 squared times the concentration of CO. And we're told that K is equal to 0.1, right? This is just given. So CO is to the first order. Okay, so I could go ahead and I could say, all right, let's say we have 2 molar NO2 and 3 molar CO. I could plug those in. I'd have 0.1. This is my K. This is my concentration of NO2. I'm going to square that. And I also have my concentration of CO. Right? This is not squared because, notice, this is not squared up here. Right? So I have 0.1 times 2 squared. That'll get me 4 times 3. Okay? This will get me 1.2. Now, the units for this are molarity per second. We'll talk about this later, but this is what we learned in lesson 7. Okay, what happens if we go from this, where we have 2 molar to 3 molar, and all of a sudden we go to this, where we have 2 molar and 6 molar? Let's go ahead and do that same thing. We get rate equals 0.1 times 2 squared times 6. Okay? I do the math and notice what happens. I doubled my amount of CO, and what happened to my rate? My rate also doubled. So whenever I have something that's first order, right? So something like a to the 1, in this case it's CO to the 1. If I multiply a by x, some value, the rate increases by x. Here I doubled it, so my rate doubled. If I increase this by 3, my rate would increase by 3. Okay? That's first order. Let's look at second order. Okay, so this reaction we say is second order with respect to NO2, right? It's NO2 squared. We already did this calculation where we said rate equals 0.1, that's our K, times 2 squared times 3, we said it's 1.2 molar per second. Let's say we now double our concentration of NO2. So now I'm going to get 0.1 times 4 squared times 3. Okay. This is going to get me 16 times 0.1. So that's 1.6 times 3. That'll get me 4.8 molar per second. Okay. Notice what happened. I doubled my concentration of NO2, and what happened to my rate? It increased not by 2, but by 4. Okay? Here, let me just show this written out instead of my choppy writing with a mouse. I doubled my concentration of NO2, and what happened to my rate? It increased by 4. And this is second order. Whenever I have something to the power of 2, if I multiply a by x, in this case by 2, my rate increases by 2 squared. That equals 4. Okay, so first order, if I double it, my rate doubles. Second order, if I double it, my rate increases by 2 squared. How about zero order? We said that this reaction, or this rate law, is zero order with respect to NO. Notice NO is nowhere in this. Okay? All right, so I've already done this. 2 molar NO2 and 3 molar CO. Notice how the concentration of NO doesn't matter, right? So what that means is whenever it's zero order, such as a to the 0, which is equal to 1, increasing it has no effect on the rate. Okay? So anything to zero order, it has no effect on the rate. Okay? All right, so you're going to do this in the next section. Okay? So we're told that rate equals K times, so for this reaction here, we're told that rate equals K times the concentration of A times the concentration of B. That means A is first order and B is second order. We're told the initial rate is 1.2 molar per second. So what happens if I double the amount of A? What happens if I triple the amount of B? And then C, or question C, What happens if I do both at the same time? Okay, so you'll do this problem and you'll see that solution later. Okay, but let's go on and let's talk a little bit about this K value. Okay? We said so far that it's just a constant, but it actually has a lot more importance than just being some number that we see on some chart. Okay, so let's say we have this equation, okay, or this rate law. We're told that rate equals K times NO2 squared times CO. Right? Those are concentrations. And we're told that we do this experiment with certain values for NO2 and CO concentration, and we get a rate. Okay? So rate K times NO2 squared times CO. Okay? So we do a trial. We're told that we get 0.56 molar per second. Rates are always in molar per second, or moles per liter per second. Okay? Just get used to that. You'll always see that. Okay. So we have that equals K times NO2. Concentrations, what we're going to be working with, are always in molarity. This will be 3 molar squared times my concentration of CO. So what is my K? Well, I can go ahead and I can rearrange this in such a way to get my K. So let's say K equals rate over my NO2 concentration squared over CO. We're going to be moving around and manipulating a lot. So, just make sure you know how to do this. Okay. Now, if this is the case, I can plug all these in. Okay, I have 0.6 or 0.56 divided by 3 squared and divided by 2.4. That's going to get me 0.026. Okay, make sure you square this number. Okay, all right, but let's look at the units. I have molarity, and then on the bottom I have molarity squared times molar. Right? This is going to be molarity over molarity cubed. Okay, molarity squared and molarity. So this is going to get me molarity to the -2 times seconds to the -1. Okay, so this is my value for K. K is not just a number, it has units. And those units are needed because rate is always in molar per second, right? And concentrations are always in molarity, right? So the value for, or the units for K are all dependent on the rate law. All right, so let's look at this one more time. So I went ahead, plugged everything in, then I rearranged, and make sure you multiply or square the 3 molar, and I get my value for K. All right? Now, the units for K depend on the overall rate order. Okay? So let's say I have a 0 order reaction or 0 order rate law. That would be something like rate equals K, and that's it. Notice there's no A to the 0 because A to the 0 is just equal to 1. So it doesn't even show up. All right, now if rate is in molarity per second, that means K must also be in molarity per second. All right, we can then go and we can look at first order. First order would be something like rate equals K times A or KB or KC. In this case, if my rate is in molar per second and my concentration is molarity, that means my K must be in units of seconds to the minus 1. If I have a second order reaction, like all of these, in all of these cases, I'd get a K that's molarity to the minus 1 seconds to the minus 1. If I have third order, I get this, right? So notice how in all of these K values, I always have seconds to the minus 1. But the power that my molarity is raised to is all dependent on what order. Okay, so why don't you do video problem 8b? In this one, I'm told that I have a rate law that's rate equals K times OH squared, right? So this is second order. So we're told that we have a value for OH, and this is the reaction rate. So we can use this to find our rate constant, K, and remember we need to use units. Okay, so do that, check out the video later, and we'll move on. Okay, so that is it for what we call differential rate laws, right? Differential rate laws link the rate of a reaction to the concentration of the reactant. Okay? We have M and N. These are my rate orders. They are not the same as the coefficients, right? So they're not based on the stoichiometry. We need to find these experimentally, and we'll do that next time. All right. Now, rate. So we have all this stuff on rate. We have units. Okay. It's in. So rate is always in molarity per second to the minus 1. We can also measure this graphically as concentration versus time. This is what we did last lesson. Okay. And here's some more information on K. Right. The units vary based on the rate order. One thing with K that we didn't talk about, but we'll talk about later, is that K varies with temperature. And this makes sense because we know this in everyday life. Baking something is just a bunch of reactions. And if I bake stuff at higher temperature, those reactions all occur faster, right? That's because K is going to change. All right, next time we're going to talk about how do we find M and N. There are two ways, what's called the initial rate method, and then by looking at integrated rate. All right, so that's it for lesson 8. Remember, lesson 8 homework is due April 29th. That's a Wednesday. But before that, we have a quiz and we have a test. So make sure you look on that. That's all on thermodynamics. All right, see you next time.